Yeah, okay. So I'm Niall Emmart. I did a PhD in big number arithmetic from the University of Massachusetts. I finished in 2018. And then I joined NVIDIA, where I worked on DL kernels and optimizations of those and big num libraries. So after that, I did some work on the Z-Prize, and here we are. So my name is Niall Emmart, and I'm the president of Urid Software as well. And I'm going to give a presentation on MSM today. And I should say I'm the world's worst public speaker. So if I don't explain something well, please feel free to interrupt in the middle of it and ask questions. Like, don't leave them till the end. It would be great if this is more of a discussion than me going through slides. Okay, so my talk has, I'm going to go over some introductory material, then the high-level optimizations. I'll talk a little bit about Gus Gutowski's MSM talk on YouTube. And then we'll look at the GPU and WASM implementations, and then how you work on multiple precision integers on like GPUs and on WASM. So MSM is an operation on cyclic groups. You have n scalar values that are between 0 and the group size, and you have n group elements, G1 through Gn. And what you want to compute here is this S1 G1 plus S2 G2 all the way up to Sn plus Gn. The MSN operation is important because it gets used in zero knowledge proof systems. It turns out to be one of the core operations for generating proof. The proof systems use elliptic curves over finite fields as the group. And I guess the typical ones are BLS and BN curves. In that scenario, the group elements are points on the curve, and the size of the group is the main subgroup order. So it's a really expensive operation to compute, and it typically represents something like 80 to 90% of the time to generate a proof. So that makes it a nice juicy target. Like if you optimize the MSN, then your whole zero knowledge prover gets a lot faster. Okay, so at a very high level, if we run an MSM algorithm and then we take a look at where the time is spent in the computation, it can be broken down to something like this. There's overhead, which is typically like 10 to 20% of the MSN time. And that's for things like pre-processing scalars, sorting, doing copying, things like that. And then the whole rest of the time is doing operations on elliptic curves. And when you do operations on elliptic curves, that pretty much just directly turns around and does operations on the finite fields. And so what you want is you want a high-level algorithm that's going to minimize the number of finite field operations you do. And the runtime is that times the average length of time to do a finite field op. So the finite field ops that you see are addition, subtraction, multiplication, and inversion. And addition and subtraction are really fast, so they don't impact the time very much. Multiplication is very slow, and inversion is much, much slower than multiplication. But the saving grace here is that inversion is done incredibly infrequently. So, so even though it's slow, it doesn't impact the average time that much. The real thing that you have to focus on optimizing is multiplication. So what I see when I look at the MSM implementations out there is people have spent a lot of time optimizing the high-level algorithms. I think because that's sort of sexy work, right? But not that much time looking at like what the compiler has generated for the big num math. And I think that if you want to have a world-class MSM solution, you need to look at both of those. You need to have good high-level algorithms, and you've got to have a great big num library underneath it. Okay, so now let's go over some of the high-level optimizations. So Gus Gutowski gave a talk on YouTube about MSM where he covers the bucket method, and that's the main high-level optimization. I sent this link out beforehand, and I hope people have had a chance to scan that, because you could spend an entire talk just going over his material, and I want to spend more time covering new stuff. But in general, the bucket method happens in 3 phases. You have bucket accumulation, then there's bucket reduction, and then there's a final MSN computation. So I guess the key idea behind the bucket method is we're going to take all of our scalars and we're going to break them into into a bunch of chunks. Okay, and then we're going to process those chunks into buckets and blah, blah, blah. This is all in Gus's talk. Okay, so let's take an example. If we're working in BLS 12377, then our field length here, this B value, is 253 bits. And if we have a big MSM problem, then we might want a C value of something like 20. So when you do that, you're going to get 12 windows of 20 bits, and then you're going to get another window with that kind of a remainder, just like 13 bits. So for the rest of the slides, here's the notation I'm going to use. N is the number of points in scalars. B is the bit length of the scalars. C is our window chunk size. W is the number of windows. And then we have I, J, and K, which are indexes. And then in order to refer to the value of one of the chunks, we'll say SI of J, which is the SI scalar and the jth chunk within it. So this would be starting at 0, 1, blah, blah, blah. And then our buckets are going to be indexed by a J and a K.
Are you assuming that the group, the points G1 to Gn, are they fixed or are they variable every time?
They're fixed. So when you start an MSM, you're provided the points.
No, but like the pre-processing, so that if you pre-process G1 to Gn, do you count that as part of the MSM time? No. Or is that an offline?
Great question. It depends on which competition, and I'll show you.
Oh, they're different places. Okay.
Yep. Okay, so let's take a look at the accumulation phase. Fortunately, these algorithms are really simple and fit on a slide. So we initialize all the buckets to 0. We just run through all of the scalars. Then we run through the chunks in each one of the scalars, and we just add the corresponding point to that bucket. And that's it. That's all you have to do for the accumulation phase. So a couple of things to note. The total number of buckets in the system is this J and SI. So this is W, right? And this term is 2 to the C. So there's W times 2 to the C buckets. And if C is something like 20, like I gave in the previous example, that means there's 13 million buckets. So there's a lot of buckets in the system. Okay, second thing.
Can you remind us one more time, what is PI?
PI is the point. So SI is the scalar and PI is the point.
Is that what you called GI before?
Yeah, I'm sorry. I changed it to PI because we're using points because we're in a BLS curve. Yeah. Yeah, good question. And each point is added to exactly W different buckets, and the total number of additions is going to be N times W.
Sorry, what's W?
W is the number of chunks.
Oh, yeah.
So it would be, in the example, would be like 13.
Thanks, sir.
Okay, so once we've done the accumulation phase, now we have to reduce all those buckets to actually get an MSM result out of it. And here's what we do. We're going to have 13 points W, one for each chunk. And what we have to do is sum from K equals 1 to 2 to the C minus 1 of K times this bucket. And Gus gives a really elegant algorithm, which makes this fast. It's called the sum of sum algorithms. And basically you go reverse through your list of buckets, and the ones that you need K times get added more because they were added first. Anyway, Gus covers that in his talk, so it's nice. If you haven't seen it, go back and look at that. It's great.
This saves the multiplication by K.
Yeah, exactly. Okay, and then once you have your 13 WJs, you scale them and you just add them up, and that's your MSM result. Okay, the next thing is
so of these 3 steps, which is the most time consuming?
The accumulation phase.
The accumulation phase. I see.
Yeah.
I see.
I mean, it would depend on the specifics, but probably the accumulation phase.
So that was the first.
The first one.
But the first, can you go back just for a second
Sure.
to the first step? So this step didn't have, oh no, it does depend on this. Yeah. Okay. Yep. Good.
Yeah. Okay, so the next thing that Gus discusses is endomorphisms, and I don't want to. I could spend a lot of time on this, so let me see if I can summarize it nicely. It turns out it's really fast to negate a point. So we can think of our scalars to start with as just having positive values in them. But because we can negate a point, now instead of having just positive values, we can have positive and negative values inside of our chunks. Okay, and that is going to allow us to save a bit in our C. So instead of having like a 20-bit C, we can do it as a signed 19-bit C. And in order to get that to work without changing it, you have to add a 1 to the next bucket, to the next chunk over. And basically, so you're recoding your scalar, so it's got positive and negatives. You haven't changed the value of it, and it in essence saves a single bit. And what that does is instead of having 2 to the C buckets, now we can have 2 to the C over 2 buckets. So it eliminates half of the buckets in the system. So it doesn't save any time in the accumulation phase, but it saves a lot of time in the reduction phase because you have half as many buckets. Now, I guess one thing, this only works if C does not evenly divide B. If C evenly divides B, then you have this problem where the top chunk can have a negative value in it, and you have no window to add 1 to above it unless you create another window out there. That's inefficient.
Actually, just to make sure, maybe the way to think about this is what you actually did is you took the numbers S and you wrote them base 2 to the C. Yeah.
Yes.
And what this says is you can actually write them base 2 to the C, but the digits are minus 2 to the C to plus 2 to the C.
Over 2.
Well, the negative allows you,
The-
minus 2 to the C, okay, fine. Minus 2 to the C over 2 to the C over 2.
Yeah, exactly.
Yeah, and
Yeah.
then right, and the negative digits are easy to handle because negation is very simple. It's very
That's
fast.
right, because now you can add a negative digit to a bucket as well as a positive digit.
Right, okay.
Yeah.
May I ask a silly question? It seems like this is related to these other kind of approaches that pre-process the scalar into, some sort of signed digit representation. I mean, frequently non-adjacent form and stuff like this. But here, there's no pre-processing of the scalar. So it seems like, well, the algorithms are very different. But is there any like useful way to think about the relationship between this kind of signed scalar recoding and the kind of non-adjacent form sorts of things that we tend to see, but in the in algorithms that aren't like Pippinger's?
Yeah, so I think this is the pre-processing step. So the code that I have here, this is pre-processing of the scalars. You do this work before you actually jump into the additions. So we're rewriting all of the scalars before we do the addition phase, before we go into the accumulation phase.
I see. Sorry, I misunderstood. Thank you. That's super clarifying.
Okay. So there's a second endomorphism in the BLS curves where you have a cube root of 1. I'm not going to talk about this slide, but the effect of it is that you can, instead of just dividing your number of buckets by 2, if you take advantage of both endomorphisms, you can divide your buckets by 4. And again, that's going to reduce the time for your reduction phase. Okay, so there were 2 questions left.
Actually, if I could ask one question.
Sure,
The
please.
second endomorphism introduces like a more complex digit recoding requirement.
Sort of. What it's going to do is if you have like a long scalar S,
Yeah.
it's going to let you cut it in half.
Yeah.
And then you have 2 points
Oh,
times
I see.
shorter scalars.
Oh, awesome. So that's ideal. That's great.
Okay, so there were 2 questions that were left open, I think, in Gus's talk. The first one is, how can we extract lots of conflict-free parallel work in an MSM? So the idea here is that suppose you have an environment where you have lots and lots of threads. You might have one thread working on S1 times P1 and another thread working on S2 times P2. But the problem is that they can conflict, right? Depending on the values in those chunks, thread 1 and thread 2 might want to add their point to the same bucket. And so that means you need a locking system and to resolve those kinds of conflicts. And on something like a GPU, that locking system is really expensive because you have to have a lot of inter-thread communication to make it work. So what we want is a way to do something to extract a lot more parallel work. And I'll answer that in a couple of slides.
And so, yeah, so I guess we're assuming we're already in the regime where the amount of parallelism exceeds the number of windows.
Yes, exactly,
Okay, I see.
exactly. So on a GPU, you need tens of thousands of threads.
Okay.
So that's not going to work.
So I have a question.
Yeah.
So the number of streaming multiprocessors on the A40G is not like orders of magnitude higher than the number of windows.
Yep.
You put conceivably put a window on each multiprocessor and try to use the warp schedule. And there's not that many warp schedulers either.
Right. I think that would be really challenging. I think you want a system where you get your parallelism another way. So that might work, but I don't think it'll be as efficient as what I'll propose in a minute. Okay, and the second question is, can we do better when C evenly divides B? Like we really want to use signed digits, and that's an important case, as we'll see. Okay, so let's talk about the GPU optimizations. So the Z prize, here's how it worked. Basically, you generate 2 to the 26th random points using the curve BLS 377 on the CPU. You can copy those to the GPU and do limited pre-computation there, which is untimed. It's not considered part of your time. You then generate 4 sets of scalars on the CPU, and we start the timers. And the goal of the competition is to minimize the time to compute the 4 MSMs of those scalars against the point set that was generated in step 1. And this runs on an A40 GPU, and we have 48 gigs of.
So what
memory.
is steps 3 again? What are these 4 sets?
So
Oh, this is just arbitrary scalars. This is where the scalars come from.
yeah, exactly. This is how the scalars
So there's
come from for the competition.
4 MSM.
4 MSMs
I see.
and 1 set of points.
Yeah. I see.
Is there any relevance to the use of 377 versus 381? I mean, obviously, I know that they have people use them for different things, but does the resulting performance look more or less the same? Does one curve have slightly friendlier properties for your purposes, or are they effectively indistinguishable?
Yeah, so there is one difference. For 381, the B value is 255, and for 377, it's 253, and that will make a difference, as we'll see.
They both have. Both of them have both endomorphisms.
Yes.
Is that just because they're it's 3 and they both have cube roots in the field, and that's enough?
It's going to come down to the number of windows. So on 381, you'd need more windows. I'll talk about it in a slide or
Great,
two.
cool.
No, it's a little bigger. Yeah.
Okay, so the next question is, how do we get lots and lots of parallelism? And it turns out it's pretty simple. So what we're going to do is we're going to pre-process all of our scalars. And every time we would have done an addition, we're going to put it in a gigantic list in memory. Okay, so we create this list, and the list is it's of tuples, I guess, and where each tuple has a bucket number and a point. And that represents an add that needs to be done in the accumulation phase. Okay, so we generate this giant list, and now we sort it. Okay, where the primary key is the bucket, and the secondary key is the point to be added. And once you sort it, now all the additions for a bucket are consecutive in that list. Okay, so now if you want to launch 10,000 threads or some gigantic number, the process is a thread goes and gets a bucket. So it says like thread 300 run bucket 699, whatever. And it can find all of the points that need to be added to compute that bucket because they're all contiguous in this list. It adds it itself and writes the result to memory. So now we don't have a scenario where 2 different threads are trying to work on the same bucket, right? Now we've assigned buckets to particular threads. And because the points are read-only, we don't have any conflicts. So essentially we have infinite, well, not infinite, but we have as much parallelism as you need.
At the expense of like a huge sort and having to have these lists.
Yes, exactly.
Okay.
Now GPUs are great at sorting though.
Okay.
So the sort ends up being like something like 10% of the MSM.
Yeah.
And the list actually fits in the GPU memory, or do you have to
Yes.
write it to main memory?
No, it all fits in the GPU memory. 48 gigs goes a long way.
Huh.
Does the size of each like sort of sub list that you send to each individual processor depend on what those scalars originally were chosen?
Yes, right. I mean, you can have a not very random MSM where one bucket is got lots and lots of points, and that could throw things off. So for example, if half of the points end up in one bucket, then there's one thread that's super busy while all the other ones are finished, and then you're just stuck.
So then in step 3, when the scalars were chosen, I think
Step
sorry,
3.
there's like some timing. Yeah.
Yeah,
How are those chosen in the competition?
they're just random.
Okay, so then you assume.
So
like,
so
even
it's
distribution.
nice and uniform. And apparently in zero knowledge proof things, they tend to be nice uniform distributions.
But even if they weren't, you could probably just rewrite the list of scalars as sort of sum of sort of two quasi-random values that add up to the non-random value. No, like it seems as if you might be able to do something like this where you produce an equivalent multiscalar multiplication that does have the property you want.
Oh, like secret share them into 2 parts and then.
Yeah, roughly speaking, right? You sort of produce something that's non-random, but or that's random looking, but ends up being what you wanted it to be.
But adds up. Yeah, you could definitely do that. And then you sum the 2 at the end. Yeah, that would work.
I see. So even if you give worst case inputs, it's still maybe a way to recover.
Yeah. Probably better to sort twice and then.
Yeah, and
just.
there are other techniques you could do. So yeah, maybe we take this offline.
Yeah,
There's a nice answer to it, but it would be long. Okay, so the next thing that we can optimize is that there's a bunch of different ways we could represent the accumulators that we need to set up. So if there's 3 different styles that we can think of. And what we want, okay, so when we have an accumulator, it's going to start out as 0. So the first add to an accumulator can just copy X and Y into it, right? You don't have to do any mod models. So that one's free. Then the second copy, we can sort of assume that the Z value is 1. So we can use an optimized set of equations for the second add. And then the third add on up, then that's where it really matters, right? Because they're going to be doing most of the additions in this category because there's lots of points in every bucket. Okay, so the obvious winner here is this batched affine addition. And we tried to get this to work on the GPU for the Z prize, but it turned out we just didn't have enough shared memory to make it work. And I mean, I spent like a month probably trying to figure out if I could get that to work, and it just wasted a lot of time. So I ended up falling back on the second best, which is extended Jacobian representation. And so this one has 10 multiplications per point addition. And once you pick extended Jacobian for the accumulation phase, you're sort of locked into it for the reduction phase. So all of these numbers come from this great website, hyperelliptic.org, which has a database of all these kinds of equations and how much they cost to run each one.
And just to be clear, so these are 3 tricks to represent points on a curve, such that the addition formula has different properties.
Right.
And you're saying you ended up using something that looks like it's 50% more expensive than the best one.
That's right.
Is there some explanation for why the best one didn't?
Yeah. So we need to do batches for that one, and you just don't have enough shared memory to put a big enough batch to amortize the inversion cost. I'll talk about that some more in some future stuff. I mean, it would have been great to be able to use this, and I tried hard, but I couldn't get it to work on the GPU. And that's kind of life when you're programming the GPU. You have ideas, you try them out, and a lot of them they look great. You think, oh man, this is going to be perfect, and you try and implement it, and it turns out to not work very well. And it, you have a limited time in the competition, so you don't get to like spend a year figuring out how to get it to work right and doing it.
And extended Jacobian is easy enough to describe, right? It's literally just every point is a triple.
I think there's 4. There's X, Y, Z squared, and Z cubed.
I see. Okay.
Yeah.
Okay, good.
Okay. How are we doing? Okay for time? Does anybody know?
Yes.
Okay, great. All right. So next question is, what's the best window size to use? So we looked at different window sizes. Here's 21 through 24. And what so this part of the table is without using signed digits. And this part of the table is with using the signed digits endomorphism. So in general, what we see is as the window size goes up, the accumulation gets cheaper, but the reduction gets more expensive. So turns out there's going to be a sweet spot, which is right here. It's equals 23. And the same thing, you see the same pattern with the, if you can use the signed digits endomorphism, where the accumulation is 7 and the reduction is 1.29, and this ends up being the sweet spot. Again, where the window size is 23 bits. But
sorry, this is a dumb question. But, when the window size is bigger, doesn't it make the buckets bigger?
size is bigger. Yeah, there's more buckets, but
There's
there's
more.
fewer points.
Oh, right, so fewer points per bucket if your window size is bigger.
Yeah.
Right, okay.
And remember, the first add is free. So if on the whole you have fewer points, you would almost think that that this would be the same across all of these window sizes because you have to add the same number of points. But the first add is free, which is why these numbers kind of change. Okay. So the scenario here is that the sweet spot is when C is 23, and 23 evenly divides 253. It's 11 windows. So we run into that problem where you can't use the recoding for the signed digits without creating a 12th window. Okay, and that's terrible. Like, let's fix that. So if we so I'm gonna, in the next slide, I'll show you a trick to fix it. And when we do that, this drops down to 8.03. And by the way, all these numbers are in billions of mod mols per MSM.
And both of these are already using a second endomorphism. So
No, so this is not using the square root of 3 endomorphism. I'll come to that in a slide or two. Okay, so here's the trick. So for any scalar at any point, minus s times minus p is the same thing as sp. You know, it's algebra, but I've showed it to a couple of people and they're like, no, that can't be right. And here's for the skeptical amongst you, here's the proof. Okay, and here's how we use it. So we're going to do a pre-processing step, we're going to go through all of the scalars that are fed into it. If the most significant bit of a scalar is set, then we're just going to replace it with minus s and minus p. And if you look at the math, minus s will not have that top bit set if it was set in s. So here's a way to produce a new set of scalars and points where the top bit is never set, and that means you never create a 12th window. Okay, and that ends up saving 335 million mod mols. So it's a nice trick.
Do you have to add minus p, like now you have both p and minus p for all the bases in the set?
No, because we've replaced the scalar and the point. So if you look at your original MSM problem, and let's say scalar 6 has a sign bit, you replace scalar 6 with the negative of it, and you replace its point with the negative of the point.
Ah, right. I'm so sorry. Yes. I was somehow thinking that the set of p was smaller than s, and yeah, my apologies.
it's good to remember.
And these the savings, that's not having to do the extra row window.
Yeah,
Yeah.
exactly.
Or do you like pre-compute the minus p somewhere?
No, it's super
Oh,
fast.
all right, it's super fast. You just do it on.
This is literally xy goes to x
Right, yeah.
minus y.
Yep. Okay. Now the competition allows us to pre-compute some points. So we do that. So for every pi in the system, we pre-compute 2 to the 46 times pi, 2 to the 92 pi, blah, 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 through all of these. Now, 92 is 2 times 46, 138 is 3 times 46, this is 4 times 46, and this is 5 times 46. And this 46 comes because our window size is 23, so this is like 2 windows. Okay, so here's how we use this to accelerate the computation. Suppose we have a scenario where we have to add pi to like window 2, let's say. So whatever bucket we were going to add that to, what we can do is we can instead add this 2 to the 46 times pi to window 0, to the same bucket. Because what happens in the MSM is the later windows, like window 2, window 3, window 4, those are going to get scaled and then added to whatever the result was in window 0. But we can do the scaling in at the front side before we add the points. And just instead of adding these up to the windows past 2, we add all these up to windows 1, windows 0 and window 1. So what this means is instead of needing 11 windows, we can get away with just 2. Okay, and that's going to save us a lot more reduction time, right? And so we end up with 7.5 billion as the final mod mole count. Now you might be wondering, why don't we have 11 copies of the points? And the only reason we don't do 11 is we don't have enough memory on the GPU to store them. So each set of points takes 6 gigs, and 11 would be 66 gigs. Don't have enough space, so 6 is as good as we can do.
So the savings here are kind of modest because reduction was already pretty cheap. And this is basically just saving reduction time.
Well, yeah, and modest is relative, right? So
Yeah.
knocking out 500 million mod mols is, it's 1/16th. It's 1/16th of the number of mod mols. So it's yeah, happy to take it. Okay.
Maybe it's not your rating. So it's like this cuts reduction hugely. If you could cut the first stage hugely, you would rather do that. But
Yeah.
we don't know.
Yeah, exactly.
Okay.
There's no other techniques besides the batch defining.
Okay. Yeah.
No, I mean, maybe there are, but I don't know them. Let's
Yeah.
let's say it like that. Okay, and the final thing is that I couldn't find a way to exploit the cube root endomorphism and save more time. So maybe I'm just not creative enough, or maybe there wasn't one. I don't really know, but it's sort of an open question.
Question, doesn't this worsen the accumulation time?
Sorry, one more time.
So you're basically moving things from window I to window 0, for example. Doesn't this worsen the accumulation time of that window?
It
Or is that
we don't change the number of points we have to add, right? We're just moving the points around. So in fact, it probably makes the accumulation phase a little bit more expensive because now we have more points in each bucket, right? And the first ad was free. So if you look at the average cost of an ad, it's now slightly more expensive.
Yeah. But like overall, this is saving.
Right. The savings you get in the reduction phase more than make up for that additional cost in the accumulation phase.
Does this increase the size of the sort or no?
No, it does change the sort though.
Yeah.
Because now whenever you are going to add to some other bucket, you need to,
Okay.
but you do need to track it all the time because you need to know which multiple of PI to grab.
Yeah.
So it doesn't change the data you're tracking for the sort.
Gotcha.
Okay, next slide. So you'll recall that the bucket reduction was the sum from k = 1 to 2 to the c - 1. In order to get this to work well in the GPU, we need to extract a lot of parallelism out of this phase as well. The sorting just gives you the accumulation phase. So there's a nice trick. Let's look at a small example where we're computing j = 0 and c = 3 with 3 threads. Okay, so in this scenario, we'd have 7 buckets. And what we're going to do is figure out that each bucket has to basically deal with, each thread has to deal with 3 buckets. Okay, so we're going to have this Q parameter, which is 3 in this. Now, for this top thread, we're going to pad with zeros, just so that all the threads are doing the same work. And what we do is each thread computes the sum and the sum of sums of their assigned buckets. Okay, so now at the end, we're going to get 3 ST values and 3 SOST values, one for each of our threads. And we can recombine them at the end like this to get the final window sum. Now, the key difference here, though, is that these sums are over the number of threads, whereas these sums are over the number of buckets. And even on a GPU, you might have 50,000 threads, but our system has, I don't know, 8 million buckets or something. So there's a lot fewer threads. And even on the GPU, like we can do another refinement, like we can add, GPUs are process things in warps. So we can reduce across the warp and only send one value back per warp, which also improves this. Like basically we can compute out some of this equation for the warp, we can do these sums as warps, and yeah, that's another step. Okay, so that's how you get parallelism on bucket reduction. Oh, and I mean, I suppose it's obvious, but each of these threads can work independently. They don't need to talk to each other in any way because they're just separate data. Okay, so there's another optimization that we found, which didn't save much performance, but I think this is really interesting from an academic perspective, so I wanted to include it in the talk. So typically when you're working with finite fields, you have these correction steps, and I'll explain that in a slide or two. And what we do is we figure out that it's possible to build some elliptic curve point routines that don't require any corrections. And I think this is pretty cool. So so we have this extended Jacobian accumulator, x1, y1, zz1, zzz1, and we have an affine point x2 and y2. So according to this website, here are all of the steps you need to follow to do that addition. Okay, and every one of these are finite field operations. So we're going to do a finite field operation of x2 times zz1, blah, 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 all the way through this. And we'll note there's sort of 4 operations that are being used here. There's multiplication, there's subtraction, there's squaring, and there's addition. Okay, squaring, of course, is just multiplication. So there's really just add, subtract, and multiply. So now let's look what a correction step is. So if we represent a finite field as a big num, right, we might want to make sure that it stays in the range between 0 and n, where n is the modulus of the finite field. So what that means is now to do an add, for example, of our 2 finite fields, we're going to add a plus b, but now we need to check if it's greater than n. And if it is greater than n, we need to subtract an n, right? So this is the correction step that we want to get rid of. Same thing for subtraction. If we do a minus b, now we have to worry about it going negative. So we check if the result was negative, and if it was, we add n to it. And then the final thing that happens is that for multiplication, we always use Montgomery representation and Montgomery reductions for our multiplies. And here there's a final check, which is if the result is greater than or equal to n, then we subtract n. So our goal is to get rid of all of these correction steps.
They're not a significant part of the computation. Oh, this is what you're saying. It's not.
Yeah, it doesn't save you a huge amount of time, but it does introduce divergencies, right?
Uh-huh.
So on a GPU, you're going to have warp divergence because some of them are going to have to do subtraction when others aren't.
Uh-huh.
So there's kind of if-thens in the code, and warp divergence. Yeah, it's not a huge cost doing this. But I think it's really cool that you can build equations that don't have the correction steps, and that's what I wanted to present it. Okay, so the way we're going to do this is that we're going to bound each of the intermediate values. And what we're going to ensure is that they're always greater than or equal to 0. For every intermediate value, we're going to have an upper bound, and we're going to show that we never exceed that upper bound. And we want to state these bounds in terms of multiples of n. So for example, if we say x is between 0 and 3.4, that really means 3.4n. Okay, so now we need a set of rules. So when you do an add in the field, obviously that result, if you do it just as a big num, will be bounded by the a bound plus the b bound. Okay, subtraction is more complicated. If we have a subtraction step, it's going to be bounded by our a bound plus the ceiling of the b bound. And the reason for that is that we want to make sure it doesn't go negative, right? So imagine the case where a is 0 and your b value has some value. We can add multiples of n to it without changing our modulus, right? So adding the ceiling of the b bound is like adding a multiple of n. Okay, and then okay, so this is, by the way, a bit confusing. So I'll give you a concrete example in a couple of slides. Okay, and then for the Montgomery multiplication, here's the rule. It's your a bound times your b bound divided by 152 plus 1. And the 152 comes from the BLS 12377 curves. Okay, for different curves, you'll have different numbers there. Okay, so here's the proof of the Montgomery bound. So Montgomery's original paper sort of showed this. If we do a Montgomery multiple of A times B, that's going to be A times B plus some Q times N divided by R. And our R in this case is 2 to the 384. Now, the thing is, we don't know what that Q is. That Q is kind of discovered as the algorithm is running, but we can say that Q is always bounded between 0 and R. Okay, so now since we're only interested in bounds, we can rewrite this in terms of our A bound and B bound. So it's A times N, comma B times N. And so here's that same equation from above with A bound and B bound instead of A and B. And here we've replaced Q with R, right? Because we're trying to show that it's a bound. We factor out an N here. We get A bound times B bound, and this should be times N over R, but we state it in terms of divided by R over N. And then this part over here just becomes a +1. And then we note that R over N is greater than 152 for this particular curve. And so now we just get this right here. And since we want our bounds without this factor of N, we drop the factor of N, and this is the rule. Now, okay, all that's fine and good, but there's something really counterintuitive about this. If we look at the Montgomery multiple bound on just some random numbers like 7.4 and 8.3, we find that when we plug those numbers in, we get 1.41 out. And what's counterintuitive is that the bound is actually smaller than the input bounds, right? So Montgomery multiplication actually shrinks the bounds. That's kind of a surprise, actually. Okay, and now we can use all of that to write our correctionless EC terms. So we're going to make some assumptions. Our x1 is less than 6n, y1 is less than 4n, z squared is less than 2n, z cubed is less than 2n. And of course, the affine points are normalized. They're both less than n. So now let's look at a bound for the first step. So u2 is x2 times z squared. And again, these bounds were 1 and 2 on the inputs. Divided by 152 is 1.02. So now the u2 bound is less than 1.02n. Same thing for s2. Okay, and now here's an interesting one. So here we have a subtraction. So we're taking u2 minus x1, but x1 was less than or equal to 6n. So here we have to change this equation to add the 6n right here. Okay, so now what's the maximum value for p? Well, it's when u2 is 1.02 and x is 0, right? So the bound ends up being the bound on A plus the ceiling of the bound on B. And that's where it comes from. Okay, if you go through all of these, you find that our output x3 here is bounded by 5.17, our y3 is bounded by 3.24, and our two z squared and z cubed are bounded by 1.02. And so now the output assertions match our input assertions. And what that means is that you can just chain these things one after another, and you know that it'll never overflow.
So there's something magical about 6 and 4? Or
Yeah, I mean, so that's just kind of playing around with these numbers, right? And seeing what works, what doesn't work. It was kind of an
it works for
iterative.
6 and 4 and doesn't work for other
Yeah,
bounds.
if you set these to 2, it won't work.
But even 5 and 4 probably.
5 and 4 don't work either, because when this x3 is probably going to be bigger than 5.
Mm-hmm.
So basically, I did this kind of process to search around and find the best numbers that actually worked. Again, it's not a huge savings, but it's a nice result.
May I ask two small things? This is
Sure.
super cool. So it looks from the prior slide like BLS 123D1 would be worse, since 3D1 is closer to 384 than 377 is. So do you end up with something similar to this, but for 3D1 it would be the bound, you'd need sort of more headroom to avoid reductions. Is that roughly correct?
No.
Yeah. There are a couple of choices. You could use a bigger R if you wanted to use this same technique, or you can change these equations around. So maybe you can't get it to the point where it's got no corrections, but you can get it so it's got very few corrections, which is
I
what we
see.
do for 381.
I see. But in 381, if you go to a bigger R, then you're also popping into a bigger multiple of 32, right? Because 384 is, well, anyway, I'm sure that, yeah, that sounds fun. Okay, so second small question. I assume that the digits here, each digit is also represented as some, set of smaller, sorry, each value is represented as a set of digits, like, whatever number of 32-bit limbs it takes to represent the finite field element. Are the limbs fully, like, is there headroom in each limb as well, or do you work with sort of fully saturated limbs?
Yeah, that's a great question. On the GPU, we use fully saturated 32-bit limbs. On the WASM, we don't. And there's more slides. I don't know how we're doing on time. I'm not really following time. Half an hour left. Okay.
So,
Yeah.
I promise I won't derail us any further, but can you avoid also doing limb-wise like carries
Yeah.
in this case too, or?
You can.
Oh, that's fantastic. Are you guys gonna write this up separately? Because I super want to read the details.
Yeah, I haven't written it up yet. That'd be a good project. Yeah, well, can you send me a message offline? My email address is in the first slide. I'll send out the slides afterwards.
Cool. Thank you.
There's a question on the chat whether extended Jacobian is equivalent to projected coordinates in terms of multiplication cost for the correctionless version.
No, I don't think so. I think extended Jacobian is 10 multiplies versus projective, which is 11. I'd have to go back and look at this doesn't save you multiplies, basically.
But the 6 and 4 might be different for projector.
That's right. Every set of equations is going to have a different
Yeah.
set of rules
Yeah.
for them. But this is probably a fairly general thing. I'm sure you can find similar stuff for other representations. Okay, then the next thing is it's easy to use 256 threads per SM. As you increase the number of threads per SM, it gets harder and harder to do the register management on the GPU. But we found that the best performance happened when you got to 384. Okay, the next thing is we use a state machine to avoid having multiple copies of the multiplier, which is fully unrolled on the GPU. Anyway, just you can look at the code that we submitted to the Z Prize if you want to see how that works. But it's important to not blow up the instruction cache. Then another fairly obvious one is you want to overlap your CPU to GPU copies. And the way you can do that is you copy the first set of scalars over to the GPU. We start the first computation. For the first bit, there's no overlap. But now, while you're computing the first MSM, you copy the second set of scalars over to the GPU. So that's happening at the same time. And then you can hide that copy latency.
But you're timed for the copy to the GPU?
Yeah, which is not negligible.
Really?
Yeah. So to copy those scalars, it's about 100 milliseconds.
Wow.
So it's expensive.
Yeah, and there's enough memory to store.
Yeah,
the
yeah, you have to do a lot of work to make sure your memory management works out and you have enough space there for all the copies of the points, 2 copies of the scalars, blah, blah, blah. There's a lot of stuff in there.
So it's copying 2 to the 26 numbers, right?
Yep. Of 256 bits.
Yeah.
Of 32 bytes, basically. Okay, and Matter Labs came up with a great optimization, which I wish I had thought of. So for the first MSM, you can actually break an MSM into multiple MSMs, right? So what you do is you just work on a quarter of the points. So you copy a quarter of the scalars, you do a quarter, then while that's running, you copy the other 3/4 and you do another MSM and you add up the 2 values that you got back on the CPU. And that shaves like 75 milliseconds off the runtime. So I really wish I thought of it. Okay.
Wait, so the GPU is able to compute while stuff is being copied into the
Yes.
GPU? Ah, okay, it's good to know.
So most of the GPU DRAM was being used by these 5 copies of the base.
Yep.
And I guess at a high level algorithm, so the threads in this case are random accessing into this huge 30 gigabyte block of DRAM.
Yes.
I see. And what do you use for shared memory? Like what is shared memory being used for in this case?
So we use async copies on Ampere, and those use shared memory to copy it into. And another thing is, and this is down in the weeds. Can you answer that offline?
Oh, yeah, sure.
Okay, let's talk about offline. There are some things. Okay, so let's go on to the WASM implementation. So the ZPRIZE WASM stuff, we generate random MSM problems, and they range in size from 2 to the 12 to 2 to the 18. And I think they do something like 200 instances. This one uses BLS 12381, where again, our B is 255 as opposed to 253 in the other one. The way they figure out how well you did is they have some baseline code, which was given to everybody, and they just measure your performance versus the baseline code, and they average it over all of the problems, the MSM problems that they ran. And there are 2 other rules. You can't use WASM vector ops, and you're only allowed to use a single thread. So, okay, so our approach is pretty standard. We use the bucket method. Our C is chosen empirically based on the size of the MSM. So we pre-compute a bunch of cut points where we need to change our Cs. We take advantage of the 2 endomorphisms, signed digits and the cube root of 1. Where possible, we use our trick where SP is equal to minus S minus P. And I think the one improvement that we have over other implementations that came before this is that we figured out how to use batched affine accumulators for both the accumulation phase and the reduction phase. And we have some nice optimizations there. So let's look at an affine point accumulation. The real thing that you get into trouble with when you do it is this inverse. So in order to just add these 2 points in affine space, we have to invert this D field value. And this inversion is really expensive. So if you're just trying to add 2 affine points, it's much cheaper to use a Jacobian or extended Jacobian. But if you have a whole sequence of them, like we're saying, add this point to this bucket, this point to this bucket, this point to this bucket, now it opens up other opportunities. And the reason is that there's a batched inversion algorithm. And I think this is originally due to Montgomery. But it's like this. If you have a list of field values that you want to invert, you can do them all much more efficiently. So what you do is you compute like the subproduct. So here's AB, ABC, ABD, all the way down the line for all of the things you want to invert. You do a single inversion here. And note, when you do that, you essentially get this product, A inverse times B inverse times C inverse times D inverse. Right? So now we can multiply this by one of the previous values that we had up here, by this ABC, to get D inverse. Right? Then we can take this inversion that we had here and multiply it by D, and that's going to give us ABC inverse. And we can just keep doing that process and basically stripping off the last guy and computing the inverse of the last guy. So if we look at the total, this takes 3n minus 3 mod mols and a single modular inverse to do a whole batch. So now if we have a batch of affine points that we want to accumulate, we can do it. Okay. So what do I mean by a batch? Our batch is essentially a list of tuples where we have a bucket and a point. And we say, this is the point we want to add to this bucket, add this point to this bucket, all the way through. We can do this in sort of 3 phases. The first phase is we generate the list of all the things that we need to invert, right? Those are the D values in that little bit of code above. The second phase is that we run the batch invert. Now we've got all our D minus 1s. And the third phase is we just complete all of those additions. But there's an important caveat here. You can't add 2 points to the same bucket in a batch. Right? If you want to add 2 points to a bucket, they have to be in different batches. But if you can pull this off, essentially now you're down to 6 multiplies per add and 1 mod inverse. And you amortize that mod inverse over the size of the batch. Right?
So this is a trick that you couldn't get to run on a GPU.
This is a trick I couldn't get to run on the GPU. And the reason is that if we look, we need all these temporaries here, and you run out of shared memory to store these temporaries. And I couldn't get around it. I spent some time working on it. Nothing worked.
Like, okay, so like, could you, like, you were like, for example, if you're computing 5 points, let's say if you're computing only 4 points, could you have enough memory to do that?
So-
Like, I'm just wondering, right?
Reduce-
So
reduce the
it
batch.
really depends on how fast your mod inverse is too. Like if you could come up with a super efficient mod inverse on the GPU, you'd need less points to amortize the cost. So it's some combination of those two, enough points plus a fast enough mod inverse.
Mhm.
Yeah. Okay, so before our implementation, the way people were generating their batches was that they were sorting the scalars and generating the lists of points to add to each bucket. So if you have that sorted, just like on the GPU, then you can construct a batch really easily. You just take one addition from each bucket, okay, and then you've got a batch. But the problem is that the sorting is really expensive. So maybe there's a cheaper way to do it, and that's what we came up with one way. And essentially, what we do is we have a lock flag for each bucket. Sorry, this is fairly obvious and trivial, but we have a lock flag for each bucket, and we have a collision list. So we start processing the scalars just in normal order, no sorting, no nothing. And as we're doing an add, we check the lock flag for the bucket we're going to add to. If it's not locked, we add that point and bucket to our batch. And if it is locked, we put that point and bucket on the collision list. Okay, we keep doing that until we either have a full batch or our collision list reaches a certain threshold size. Okay, at that point, we run the batch. Okay, and then the next step is we reset all the locks and we process the collision list as follows. We go through the collision list, and we just start adding those collision points to our new batch,
Yeah.
as long as we don't have collisions. If we have collisions, we leave them in the collision list for the next iteration. And we repeat that process until we've gone through all of the additions that we need to do and our collision list is empty.
How big were your batches?
So they're configurable. I think we use 1K and 128 for our collision this size. But it could have been 4K. I don't think it really makes that much difference whether you're amortizing over 1K or over 4K. It's down in the noise.
So if you have five elements in the collision list to collide, they're going to take 5 rounds to clear.
No, maybe, oh, if they all collide with each
Yeah.
other, yeah.
So-
But that's not really what happens, right? Usually they're,
oh, it's just pairwise collisions.
yeah, they're just pairwise collisions.
Okay.
Right. And also the collisions are the rare case. So having this collision list stuff is only to make sure we get a correct result. It really doesn't get used that much in a real MSM.
Do you like have any sense about like what fraction of time goes into sort of normal operation, building batches and clearing them versus like at the end clearing out like the deepest collision list?
Well, the collision list is processed on every batch.
Yeah, you know, so
Right.
eventually you get through all your points and you just have like a few outstanding collision lists that you need to drain. And you're not doing any batching or very much
Oh.
batching at this point.
I think that's trivial
It's
at the
very
very
small.
end.
Okay,
Yeah,
yeah.
that tail is tiny.
Tiny, okay.
Yeah. But you are clearing out the collision
As
list
you go, yeah.
as you go all the time. Yeah, so this has a lot less overhead than sorting for sure. But I haven't calculated out the overhead, actually. Like I don't have a percentage number,
Yeah.
but it's quick. Okay, and the last thing we want to do, which I haven't seen any other MSM implementations, is use the affine batches for bucket reduction. And we just steal the same idea we had on the GPU. Instead of these things being threads, these are just groups now. And you can take one addition from each group and create a batch that way, right? And that reduces the number of points dramatically that you have to add at the very end using an extended Jacobian. Okay. So that's pretty simple.
So
Okay.
These methods actually beat the extended Jacobian. So it's better to use affine with batching than extended Jacobian.
Yeah.
Because you almost get it down to like 5 multiplications, you were saying.
6, yeah, 6, yeah.
versus 11 or 10.
Yes, exactly, 6 versus 10. So it's 40% faster.
Yes. Maybe you said this in the video, sorry. Roughly what order of math, like how much slower is an inversion in the WASM?
I think it's like 20, I don't know, 10 to 20 multiplies is nice. Stick your finger in the air number.
Yeah.
But again, I think it depends. Sometimes people go for constant time inversions,
Uh-huh,
and those are slower.
I see. And constant time is not a requirement.
Not a requirement, yeah. Okay, so just a quick summary. I think there are 4 things which we haven't done literature surveys on, but I think they're potentially novel anyway. So the correctionless EC algorithms I think is cool. The S equals minus S minus P trick is cool. The collision method for generating the batches on WASM is neat. And then I think the batched affine accumulators for the reduction phase. So those are the 4 things that I think are kind of interesting from the work. Okay, guys, we're getting near the end. Sorry, this is such a long talk.
Actually, maybe before we do that, I was gonna ask, so, you know, these things are used to commit to witnesses. So that's where the MSM comes in. The MSM is used as when you commit to secret data.
Okay,
So actually, if I was thinking about this at the beginning, that if the time to run the algorithm depended on the data you're committing to, then there's a timing side channel. So what part of your algorithm would you say are time dependent? So I guess in the GPU case, there's no inversion. So in the GPU case, is it constant time or is it still?
no, I think that's a good question.
So by the way, I'll say that getting rid of the ifs in the Montgomery, that's crucial for making things.
Yeah,
done.
for
In
side channel stuff.
In
Yeah,
fact, there's an old paper that shows that the if in the Montgomery.
yeah, you can side channel
you can side channel
and RSA.
Exactly.
Yeah.
The issue is the lists, right? Like per thread are going to be scaled differently according to the original scalars.
Yeah.
And so maybe Riyad's suggestion of doing like the secret share thing, but then
Oh,
you increase the cost by twice.
Right.
So,
Yeah.
Are there other parts that are time dependent or the data dependent?
So I think if you have 0 points in a bucket, that might be observable in the runtime. But I'll also say GPU runtimes are noisy. So it's
No, that's not a defense. Because I would just run you multiple times.
yeah, maybe. Yeah, I mean, they are really noisy though. I'm not,
So we really run you multiple times.
yeah, you'd have to do a lot. You'd have to do a lot.
I mean, the secret share.
Yeah, that would prevent it, but the question is whether that was the only source of data dependence in the time.
Again, I think you can maybe observe it a tiny bit, because depending on how many buckets are empty, you can maybe observe that,
Mhm.
right? Because an empty, if a bucket is empty, that means some bucket has more points.
Yeah.
And
Yeah, that's
the later additions cost more than the earlier additions. You could fix that pretty easily by always using, by never optimizing it like that. You could always do 10 multiplications per add, and then that would get rid of that.
sure, yes.
That would get rid of that. It would cost a little bit of performance,
Mhm.
probably 10% or
Oh,
so.
so you're saying that making a time constant time actually is not that expensive?
Right,
I see.
might be 10%.
Oh.
Right, because then every bucket has something. Even if it doesn't have something, every point has to get added to a bucket, and
Right.
as long as it takes the same amount of time, no matter which bucket it's added to, you're all set.
I see. That's pretty interesting, actually. Just for safety, you might want to have a version of the code that is time independent.
So then the other question would be, is sorting in any way data dependent? I don't know the answer
That
to that.
depends on your sorting algorithm.
Yeah, I don't have an answer for that. It might be,
I see.
it might be, yeah. So
Interesting.
maybe you
Okay.
need to write new sorting stuff,
Right.
which is not data dependent.
Right.
Well, also it seems like when you're doing this on the GPU, like scheduling, like leaks some information about which like, it seems like what threads have like a longer work list is going to depend on the actual values of the scalar digits.
Yeah. So
Yeah,
So I kind of glossed over this, but we actually do 2 sorts. The first sort is generating the bucket lists, and the second sort is ordering the bucket lists so the biggest buckets go first.
yeah.
Okay, so what happens is that means by the time you get to the end,
Yeah.
all the buckets are sort of the same size,
Gotcha.
and the big ones get hidden.
Mhm.
Yeah.
And the reason we do that is we don't want tail effects.
Of course,
We
of
don't want
course.
some like just
Yeah.
random thing happening where you get some giant bucket at the very end, and that slows down your whole computation. So we sort them to run those first. And also sorting them in that order means that you get better warp convergence, because that means all the threads in a warp are running the same bucket size
Hmm.
in general.
Oh, interesting.
So that's the other savings.
Cool. That helps a bit.
Okay, so I promise we're getting near the end. I'm so sorry it's so long. This next section of the talk is about how we actually work on the big nums on the GPU and in WASM. So on the GPU, we represent a BLS 377 field as a sequence of 12 32-bit limbs. Okay, and the GPU is a 32-bit processor, so that works out great. The key thing that we want to do, though, is make sure that all of the finite fields that we need to work on, like all the fields for an accumulator, plus all the fields for the points we're loading, all the temporaries that we're generating, all of that stuff has to fit in registers on the GPU. And you have to design your code somewhat carefully to make sure that that actually works. If you don't, then what will happen is the GPU will start spilling to local memory and your performance will just fall off a cliff when that happens. Okay, so the addition and subtraction are linear. They just take 12 operations, one for each limb. And what we're doing is we're leveraging the carry flag on the GPU to chain the carries along as we're doing the adds. The GPU has really good carry handling instructions. So it's actually a really nice architecture for multiple precision stuff. The two expensive operations are the modular multiplication and the modular squaring. These both use Montgomery. They're fully unrolled, which means that, because these things are in registers, in some sense, they have to be fully unrolled, right? You can't do indexing on registers on the GPU. And these things end up being something like 400 instructions in length for a mod mul and about 320 for a mod square. Mod squaring is a little bit faster than mod mul because there's some tricks you can take advantage of. And I guess there's one other optimization which I didn't have anywhere else to put in, so I stuck it in this slide. Matter Labs found something pretty cool, which is that if you're doing A times B plus C times D, the right way to do that is you multiply your A times B, you add your C times D to it here, and then you do a single Montgomery reduction on the combined value. And that saves a Montgomery reduction step. Okay, so underneath the covers, you write your code on the GPU. The code gets compiled down to the PTX, and then the PTX gets compiled down to specific instructions on the architecture that you're running it on. So whether it's Volta, Turing, Ampere, each generation has a different ISA. Okay, but it turns out that the multiplier has been not changing in the last couple of generations. So all the GPUs after Volta have an IMAD wide instruction. So it takes 4 arguments. This is the destination. We have, and then 3 sources, A, B, and C. And the way this instruction works is we got 2 32-bit values. They get multiplied together to generate a 64-bit result. Okay, and that 64-bit result is added to a 64-bit C argument with an optional carry in and an optional carry out. And then that writes a 64-bit value to D. Okay, the GPU is really fast at this instruction, by the way. It completes 128 of these every somewhere between 4 and 5 cycles, right? So this is really fast, especially considering it's a 32-bit architecture, right? You're getting a 64-bit product every 4 to 5 cycles. But there's a rub. So I think when they designed the ISA, this seemed obvious that if you have a 64-bit value, it's going to be even register aligned. So the low part of the 64-bit value is in register R, and the high part of the value is in register R plus 1, right? And R should be an even number. I mean, they probably did that without. I mean, that was probably a natural choice. But it comes to bite us when we work on multiplication. So here are. Okay, on this slide, I'm not really showing all 12 limbs. Here's much truncated values. This is a 4 limbs times a 4 limbs. The real picture should be 12 limbs times 12.
You're not using Paratuba for this?
No.
For 12 limbs, it doesn't.
No.
value?
No.
Okay.
It's a good question, but no, I don't think it does. Okay, so so here's the products that we need to generate. So this is A0, B0, and this is the low word. Here's the high word for that A0, B0. Then here's the low word for A2, B2. Sorry, A2, B0. Here's the high for A2, B0. And here are the odd ones, right? So here's A1, B0 and the high of A1, B0, and the low of A3, B0 and the high of A3, B0. So these two rows are all the B0 terms. These two rows are the B1 terms, the B2 terms, and the B3 terms. Okay. So now we want to accumulate all these values into a set of accumulators down the bottom, right? And we want this one to be an even, an odd, an even, odd, blah, blah, blah. Here's the problem. So these red terms are actually trying to accumulate a low product into an odd register. And we don't have an instruction to do that. The instruction on the GPU allows for a low product to be accumulated into an even register and a high product to be accumulated into an odd register. So you can easily write an algorithm that tries to do this step in CUDA, but when the compiler gets it, it says, hey, I don't have an instruction for that. And it generates like, I don't know, 5 or 6 instructions to deal with the fact that it's not aligned properly. Okay, so all these red terms turn into awful code, even though these other black ones are great. Right? And you'd never really know this. Like you could write this algorithm in CUDA and not really understand the implications of it until you actually go through the assembly that it generated, that it's actually running on the device. And the assembly that the final instructions that it's running, there is a little bit of documentation, but there's not, that's considered an NVIDIA secret thing. And there's not lots and lots of documentation on how they work and what their capabilities are.
Right, so even at the PTX level, you wouldn't see this.
Even at the PTX level, you do not see this. The PTX level, it shows you each of these lows and highs. So
So
you don't,
how did you discover the problem?
well, I worked for NVIDIA.
Oh.
I wrote their big num libraries.
Insider secrets.
So there is a solution to it though. Okay, so what we're gonna do is these terms that are black, these are all the ones that were even aligned. And we're gonna set up one set of accumulators for those. And all these things that were odd aligned, we're gonna set up a different set of accumulators for those. Right, and we're just gonna cheat, like this is, you notice how this is an even register under an odd register. But then after we get these two sets of accumulators, we're gonna shift the odds by a word and add them all together. And we get our result. Okay, the next thing I want to talk about is the fast scoring. I've mentioned this a couple of times. So the idea here is that if you look at what comes out of an A times an A, right? You've got these red values and you've got these blue values. And it turns out if you look in any individual column, the reds and the blues match. So here we've got a low of A1, A0. Here we've got a low of A0, A1. Here we've got a high of A1, A0. Here we've got a high of A0, A1. So the reds and the blues match in every column. So the trick to accelerate this is you just compute the red products. Okay, you get all those accumulators, you double that value, and then you add the gray diagonal. And that means that you can do a square in something like half the time of a multiply. Now, even after you do this, you still got to run it through a Montgomery reduction. So at the final end of the story, a modular square is roughly 80% of the runtime of a modular multiply. But that's still something you want to take advantage of, right? I mean, there's a lot of squares that you have to do. Okay, so the key takeaways, I don't care whether you're working on a GPU or something else, you really need to have a deep understanding of what your hardware that you're targeting, right? If you want to build a good big num library, you need to know what your architecture is and what its weird restrictions are. And all these different architectures have tons of weird restrictions. Even if you're running on an Intel processor, right? Like it generates x86 code that gets translated into something that you can never see that's run in some internal micro thing. So, who knows what it's doing? Yeah. Okay, whenever possible, you want to write in the lowest level you can. So if you can write something in assembly, you should for these big number routines. And when it's not possible to get all the way down to assembly, like on the GPU, you really want to be disassembling what the compiler is generating and taking a look to see if it's doing sane stuff or if there's anything like really ridiculous there. And I would also say you should have in your head, a mental model of what you think it should be generating, like how many instructions, and you should go back and check the counts. Like that's really the key thing to do. And the final thing is that for a lot of these big num algorithms, there's lots of subtle variants, right? Like Dan was saying, you know, why aren't you doing Karatsuba? So you should try it. You should try Karatsuba. You should maybe even think about Tum Cook or some of the bigger things. You have to do a lot of experiments and just kind of rule things out and say, well, this is slower, so I'm not going to use it.
And you tried it and it doesn't work, it doesn't help.
Yeah, it's you end up fighting with the compiler. I think in theory, you can do Karatsuba faster, but you can't get the compiler to generate the instruction sequences you want. Yeah, we could talk about it more.
Okay.
Okay, so that's it for the GPU slides, and I just have a couple more on the WebAssembly stuff. Getting to the end here.
Yeah, actually, I have a question that it might
Sure.
be better at the end. I was just curious, like, if you had some numbers around the overhead that these techniques have for like small numbers. I know that's like a weird question, but like, is there kind of a point where the naive method is more efficient versus like some of the tricks?
Yeah, there is not a one answer fits all. So it's going to depend on your architecture, right? So you'll get different crossover points on WASM than you will on for example, the GPU. And so in my WASM stuff, I found that one level of Karatsuba was faster, but I didn't find that that was the case on the GPU. So you have to try it on different architectures. If you're running really small numbers, then I think you always want to stick with the naive grade school method.
Yeah, well, there's like settings where sometimes it's small versus big, so it's like it's nice to be able to say like, oh yeah, at this point you definitely use
Yeah.
this, but
I don't know. I think you have to check it on different architectures. And it's time consuming to do this work, right? So this is not sexy stuff like optimizing the high level algorithms. So I think people, when they write their MSM implementations, they ignore this a lot, and you can't. not if you really want a great MSM. Okay, so in the WASM environment, I thought I'd talk a tiny bit about the workflow. So you start with some C source, you run it through Clang, it generates a WASM file. The WASM is a bytecode, kind of like the Java JVM. And it gets consumed by Chrome and maybe lots of other tools now. So the JavaScript really manages the loading of the WASM code and the interface between WASM and your web page. But under the covers, Chrome has a bunch of compilers and interpreters. So at the beginning, it might be interpreting your WASM bytecode. But as that runs for a while, there's another compiler running in the background called Turbofan, which does just-in-time compilation, taking that WASM bytecode and turning it into native x86. But the problem is whoever designed the WASM stuff, in their infinite wisdom, they left off carry flags. Okay, there are no WASM instructions that deal with carry flags. And that's really tragic for big num developers because big num stuff wants to carry flag all over the place. And so what that means is because of this process, right? So WASM doesn't have any carry flags. So that means when it gets translated into native x86, guess what? No carry flag instructions. Okay, so to work around that, what we do is we represent a finite field. This is in 381 as 13 limbs of 30 bits. Now, normally this would be 12 limbs of 32 bits, but here we use 13 limbs of 30 bits. And we put each one of these in a 64-bit unsigned int. Yeah, I think the rest of the slide is pretty obvious. I talked about this. We do one level of Karatsuba in the multiplier, and we take advantage of fast squaring for the mod square. Okay, so let's look at why we use 30 bits. So suppose for a second that we had done, okay, so backing up. So in general, for these multipliers, what we want to do is sum down one of these columns, okay? Now, if we had chosen to use 32-bit limbs, then 32 bits times 32 bits is a 64-bit number. And then here we would be getting another 64-bit number. And when we add those together, there's a chance to overflow an unsigned 64-bit int. So then you have to have instructions to catch that overflow condition, which are really messy, right? Like, because you don't have a carry flag. And propagate it to the next column over. By using 30-bit limbs, though, you multiply two 30-bit limbs, you get a 60-bit number, and you can accumulate 16 of those without ever having to worry about overflow. So, so it turns out that the overhead of the extra multiplications that you have to do because you're using 30-bit limbs is cheaper than having all the instructions to catch the overflow conditions. Okay, so let's look at how some of these things are actually implemented. If you do adds, it's just a component-wise add. Okay, but the result now, instead of having 30 bits, now we have 31 bits potentially in each limb. So we have to have some kind of carry resolver. And basically the way this works is you run through all of the limbs, you get the carry part out by shifting it to the right 30 bits. So you can think of it as sort of having a data part and a carry part. The data part is the lower 30 bits. The carry part is that next 34 bits. So you pull that off and you add that to the next limb. You go all the way down to limb 12, and then you just mask them off at 30 bits. And you don't have to mask the 12th limb. So don't bother doing that. And subtraction is slightly more complicated. Here we want to have an assumption, right? So we want to know that our B value is less than some multiple of n. In this example, it's 2n. So what we do is we take our result limb, which is our A limb minus our B limb, plus that 2n value. And this 2n value has been written in such a way that it's guaranteed to always be greater than this B limb. Okay, basically what we do is we subtract some bits off of the next one. Sorry, this is a little bit in the weeds and confusing, but the idea is that we don't want any of these limbs to go negative, right? So we want to make sure that not only the whole number remains positive, but each of these individual limbs stay positive. And we do that by using a different version of 2n than you might otherwise see. These are 32 bits instead of 30 bits. But when you run the resolution algorithm on this value for 2n, you get the actual 2n. Okay, and thank God that's the last slide.